talk about AGN feedback in elliptical galaxies with AXIS. This is something that I've been looking at along with the AXIS Galaxies Science Working Group, some members of which are in the audience. So just to outline my talk, this is really just a summary of the points that I'm going to make. That Chandra's view of AGN feedback has necessarily focused on the nearest, richest galaxy clusters. I'm thinking, of course, about Perseus and M87 and Centaurus, all of which are spectacular. But the evidence for radio mode feedback in individual galaxies, so beyond sort of just Virgo ellipticals and galaxy groups, has been much more limited. A lot of this has been driven by ACES's loss of effective area at low energies, and I'm going to go into all of this. But then I want to really focus on what AXIS is going to be able to do, the fantastic expansion in sensitivity that we're going to have, particularly at soft energies, the spatial resolution, and together these two are going to reveal feedback in even sort of the tenuous hot atmospheres of individual ellipticals. So just to sort of go a little bit into introductory material for those who aren't familiar with this, and why we're sort of interested in it. So ellipticals of Milky Way mass and above are surrounded by hot, diffuse atmospheres. Typical temperatures for these 10 to the 7 Kelvin or lower, and they're very diffuse. So we have low densities, 10 to the -1 to 10 to the -3 particles per cubic centimeter. We have low densities hot plasma. For lower mass systems and for spiral galaxies, they can also have hot gas, but the fraction of baryons within the virial radius tends to be much lower. They're much more tenuous and they're much fainter. So really, I'm sort of focusing on those with hot atmospheres in this talk, but we will be able to detect the others as well. So this is a series of images here from Norbert Werner's fantastic paper, where we're looking at nearby massive ellipticals here. This is just the optical pictures. This is the stellar light. You can see all the sort of reddish stars in here. But then if I put the Chandra images over the top, you can see that for the same field of view here, we now have distributed emissions. We have this kind of diffuse emission, and then a huge number of point sources in here. We have a lot of X-ray binary sources. And I think for at least a few of these, we have nuclear point sources as well, non-thermal emission from the AGN. But we're not just looking at, spherical hot atmospheres, hydrostatic hot atmospheres. You can see they're clearly perturbed. And this is all down to activity from the central AGN. It's producing, you can see fantastic structure in here. We've got all kinds of, Mike, can you see my cursor? Does that work?
Yes. Yeah, I can see that.
Okay, cool. So we've got kind of cavities in here. Each one sort of few kiloparsecs across in these systems. We've got these kind of bright rims in NGC 4636 down here. And again, cavities really rather beautifully in NGC 5044. So there's a huge amount of structure in these hot atmospheres. And I can show exactly what's doing this in a bit more detail if we look at the example of M84, because this has got a really nice series of images that shows this really quite beautifully. This is from a paper earlier this year by Chris Bambick. So on the far left is the optical image. We're looking at, again, at the stellar light from M84, massive elliptical in the nearby Virgo cluster. Then in the central panel, exactly the same field of view, we're now looking at the radio image from the VLA. We've got the central supermassive black hole in the middle of this elliptical, and it's throwing out these huge radio jets to the north and south, and they're hitting surrounding medium, they're getting disrupted, and we've got these beautiful big fluffy radio lobes or radio bubbles that are forming here. So there's a huge amount of activity from the AGN. And then the X-ray image on the far right showing us the hot gas atmosphere is then showing all of the energy getting sort of pumped into the galaxy's hot atmosphere. We're able to sort of see the imprints of all this activity and all the work done on the gas by looking in the X-rays. And again, you can see we've got kind of distributed diffuse emission here, lots of these point sources, X-ray binary sources, and then there is also a nuclear point source here that you can't quite see. M84 has got this fantastic H structure with its sort of diffuse gas. We've got these kind of filaments coming up and down in this sort of H-like structure. And if I put all three of these pictures now together, you can see that this H structure is coming round the radio lobes like this. We've got this sort of, the gas has been pushed aside and compressed and now forms these kind of beautiful rims and sort of tendrils around all the radio lobes where they've sort of pushed all of the hot gas aside. So what we're looking at is radio jets and lobes inflating these bubbles in the hot atmosphere. They pop out as X-ray cavities that then filled with radio emission when you put the radio observation over the top. And the great thing about studying feedback with X-rays is that we can measure the energy injected by all of the AGN activity. We can look at the work done essentially on the hot gas. For relativistic contents of our bubbles, this is 4 times the gas pressure of the surroundings that the lobes are inflating against, times the volume of the bubble, where we make an assumption that it's a spherical or an ellipsoidal structure. So we can get this measurement of the amount of energy being injected to the gas. So the wider sort of picture here is that really what we want to understand is how all of this activity is slowing down massive galaxy growth at late times in the universe. All of these energetic outbursts from the AGN are pumping in a huge amount of energy to the surroundings. They're heating the gas, driving gas outflows, and they're suppressing star formation. And really the sort of scope of this is best shown by this plot here, where on the y-axis we've got stellar mass as a function of halo mass, so number of stars per unit of mass of our halo, or sort of equivalently the efficiency with which baryons are forming stars in these halos, as a function of halo mass along the x-axis here. So we've got rich clusters up at the top end, and then we've got Milky-Way mass galaxies somewhere in the middle, about the sort of inflection point here, and then we've got low mass systems right at the bottom. So you can see the grey dashed line with the squares on it. This is where we've got essentially only gravity in our simulations, and we're forming stars really, really efficiently. Everything, all gas clouds are collapsing. There's nothing to sort of counter this, and we get loads and loads of stars forming in all sort of halo sizes. The reality, of course, is the lower set of curves here. We've got much less efficient star formation, and the reason for this is there's a huge amount of energy going into these systems from stellar feedback at low masses, and then AGN. We need the sort of bit more oomph to counter collapse in the more massive systems. So we've got a huge amount of feedback, and it's thought to be really shaping the structure of galaxies at late times. So all this kind of process of AGN feedback is included in all simulations of structure formation now, but it's sort of given more or less an ad hoc kind of tuning because we don't really understand how all of these things work from first principles. We don't sort of know about how much energy typically gets injected in all the different channels that it gets injected in. As sort of a function of AGN activity and so on. So we really need a much more comprehensive understanding of how AGN feedback works in order to be able to put this particular bit of physics more usefully in our simulations. And our current understanding is really sort of predominantly shaped by observations of the nearest richest galaxy clusters, where you can see this happening in greatest detail. So I'm showing the Perseus cluster here as the most famous, of course, example of this. So we've got the optical image on the right-hand side. We're looking at all the galaxies at the center of the very rich Perseus cluster, including right at the center, the brightest cluster galaxy, NGC 1275, which has got all these beautiful H-alpha filaments and blue star formation happening at the center here. On the left-hand side is the Chandra image, again, same field of view. And we're looking at all of the AGN activity in the hot atmosphere, which just shows up so beautifully in this image. We've got a nuclear point source at the center, and then we've got cavities. You can see cavities further out. And then in addition to this, in addition to these series of these bubbles, we've got weak shock. The weak shock, I think it's that one there. the sound waves. There's all kinds of ripples throughout this image, which are sort of sound waves propagating out. There's turbulent structure in here. We've got all these beautiful filaments as well of these gas flows being pulled out by all this activity. So there's a huge amount of detail in here. It's an incredibly complicated system. And really, you know, this is what we need to be studying when we talk about AGN feedback. We want to be getting into all of this detail. But generally, Chandra, what we've been able to do is look at radio bubbles in a large number of rich clusters. And the most surprising result that came out of this was just how finely tuned feedback appears to be. The AGN don't over or underheat their surroundings. There's actually this beautiful correlation between the heating rate supplied by the AGN, by the cavities when we measure the work done, versus the gas cooling rate in the hot atmospheres. We're trying to suppress this, of course, to prevent star formation. So this is this plot from David Rafferty's work in 2006, looking at rich clusters and all of the energy injected by the radio bubbles, and found that essentially they're lying along this one-to-one line at the center here. So AGN feedback is really quite carefully tuned to the cooling rate, which is just incredible, really. What we want to be able to do, of course, is look beyond these really, really rich cluster systems. We want to be able to look at individual galaxies. Of course, the sort of bulk of the stellar mass in the universe is in these much more commonplace lower mass systems, not in the rarer rich cluster systems. We want to see if all these processes are scaling down. Does feedback operate with similar efficiency to that found in clusters, but on the really short gas cooling timescales, the really challenging timescales of individual galaxies? And there have been attempts to do this with Chandra. So I've got two plots here from studies by Paul Nelson and Electra Panagoulia, where they were looking specifically in the Chandra archive at lower mass systems. So again, these are the plots of heating rate versus cooling rate, cavity power versus gas cooling rate. And they actually found conflicting results. On the right, the Nelson plot shows a deviation at the sort of low mass end, where he found that cavities were less frequent in elliptical galaxies, and they tended to be that more powerful, suggesting that there was more intermittent, powerful outbursts, and that the balance was a bit disrupted. Electra Panagoulia's study, she looked at a wider sample, but I've sort of highlighted the low mass part of her study down here, and she found, in fact, that the cluster processes were scaling down, that this balance is maintained. So this was sort of the state of the art then with Chandra. But obviously we're looking at a small sample. In each case, for the low mass systems in particular, there are large uncertainties because these are fainter systems. We've not got as many photons. We can't constrain the gas properties as well, and it's likely because they're fainter that we're missing some outbursts as well. The systems that were studied are mainly galaxy group systems, some Virgo ellipticals in here as well, but we're really not looking at the kind of huge sort of representative individual galaxy sample that we really want to do for this. Unfortunately, this science is really now completely out of reach with Chandra because of the loss of ACES's effective area at low energies. This is a plot here from the Chandra Observing Guide showing you the ACES spectrum of a rich galaxy cluster. And you can see different epochs of the observation. Here we move from the year 2000 to 2021. And you can see the count rate just drop away in the soft band here. I really hate looking at these kinds of plots, but this is what has happened. So it's over 2 orders of magnitude down here. We've lost effective area at half a keV from 300 centimeters squared at launch, now only a few centimeters squared, which is heartbreaking. This is due to a buildup of a molecular contaminant on the ACES optical blocking filter. So this is the situation, and the soft band is exactly what we need for these individual galaxies. This is I really like this colourful plot. This is from Jeremy Sanders' review paper in 2023. And what you're seeing here is as the temperature of hot atmospheres drops down, we shift from the blue to the red and the pink. and we just squash all the emission down into the soft band. So this is where we need to be looking for our individual galaxies, and this is exactly where we've lost our effective area, which is very sad. But it brings me on to talking about AXIS. And this is a much better kind of plot because it shows the impressive, expansion of soft response we would get with AXIS, which would just be absolutely fantastic. So I've got on-axis effective area against energy here. And you can see the black lines are Chandra. So Chandra at launch is the solid black line. And then the dashed line is Chandra currently. You can see the reduction in the soft response. And then the blue line is AXIS. And what we would have with that, and you can just see the dramatic expansion of the soft response here, which would be just absolutely ideal for looking at these individual galaxies. But it's not just the soft response. We need the high spatial resolution as well to be able to resolve all this complex structure that we see with AGN feedback. And AXIS will actually have this across the full field of view as well. So you can see in the plot on the left-hand side, this is point spread function against off-axis angle. So as we move away from the at the focal point, we still maintain a small PSF. Whereas with Chandra, of course, as I'm sure many of you are aware, as you move away from sort of the central 2 arc minutes, the PSF grows dramatically and you lose all of this fantastic detail. So the Perseus images, we've got the Chandra PSF over the sort of central few arc minutes, but then you sort of very dramatically lose all of that detail as you go even a little bit further out, and you end up having to do multiple pointings to be able to see the sort of detailed structure. We wouldn't have to do that with AXIS. You'd get the full field of view of 24 arc minutes, and you'd sort of open up all of this in really only short exposure times. We also need we need specifically the high spatial resolution for elliptical systems, shown by this plot on the right here. This is another plot from Elettra Panagioulia's paper, showing how the size of X-ray cavities comes down as we move to lower and lower gas temperatures, lower mass systems. So we do need and we do need the high spatial resolution to be able to probe AGN feedback specifically on the scales for individual galaxies. So what would we want to look at with AXIS? So first off, we want to look at the Atlas 3D sample of nearby ellipticals. This sample comprises all the nearby massive early type galaxies. The original paper on this was Capillare et al. 2011. So there's 260 targets in total, all within 42 megaparsecs, and covering the mass range that we'd be particularly interested in covering. 60 of these targets have so far been detected with Chandra, and that's what I'm showing in this plot on the right here. We've got the flux of the hot atmosphere on the y-axis, gas temperature as sort of a proxy for mass on the x-axis here, and all 60 of these systems, I think I plotted on here, the ones that have got nuclear radio sources, so clear evidence of AGN feedback or AGN activity, are shown by the red points here. So I've labelled many of the sort of popular ones from the Chandra archive that Chandra has sort of been able to do in detail, and you can see they're all in the top right of this plot. These are all the bright systems that Chandra has been able to study feedback in, whereas really most of the systems are not really quite that rich, and they're much more down in the lower left part of this plot. So I've plotted on the top here, the blue bands are the Milky Way's, the temperature of the Milky Way's circumgalactic medium. So we've got a warm component for that and a hot component, but this is the kind of range we want to be in. These are the kind of systems comparable to the Milky Way that we want to be really studying. I should say the uncertainties, I haven't plotted them on here because it would just make the plot too confusing, but they're really substantial for these data points in the lower left, up to sort of 80% uncertainties, obviously much smaller for the ones top right, but there are substantial error bars on here that I haven't shown. So these are the systems we're really interested in. If we want to do feedback studies with AXIS, then I've got typical exposure times that we'd need as these sort of horizontal dashed lines here. So 10 kiloseconds with AXIS up here. This is equivalent to about 250 kiloseconds with Chandra at launch, 2.5 megaseconds with Chandra now. This is just as a result of the fact these are such low temperature soft systems. So really, as I say, this science is out of reach for Chandra, because the sort of minute you start going further down, it just becomes prohibitively expensive. But with AXIS, very doable snapshot observations, and we could get a fantastic sample of these systems. So what would AXIS see? Well, I'm just sort of considering an example object of NGC 524 in here, which is this data point here, half a keV temperature for the hot atmosphere, and it's about 20 megaparsecs away. The Chandra observation of this target was 20 kiloseconds in 2006. The date's really crucial because this is before most of the contaminant buildup. So this was still when Chandra was really quite sensitive. That observation got 400 counts in total, so enough for a global temperature kind of measurement from that. AXIS in 20 kilosecond will get more like 12,000 counts with just this snapshot in total. And what we'd actually do in reality, rather than doing that, would be to divide it up into a whole series of annually and produce radial profiles in the gas properties, each with a couple of thousand counts in. And we get spectra something like this. I'm showing here, this is an AXIS simulation for a couple of thousand counts on this particular target. You can see we're detecting it above the soft background and everything here, and we get good constraints on temperature, a sort of few percent accuracy with this. So what's the difference then? If we're moving from a few hundred counts with Chandra to more than 10,000 with AXIS, why is this such a game changer? Well, it really is in terms of feedback studies, as I've tried to sort of show here. I'm using NGC 5813 as an example. Obviously, Chandra has done a very deep study of this target. And I'm only showing a tiny snippet of the data for my purposes here. If you're interested in this object, Scott Randall's paper in 2015 is what you want. But these are two little snapshots of NGC 5813. The one on the left is demonstrating what you can do with 400 counts with the equivalent of the Chandra image. And really, I've had to heavily smooth this for you to be able to see anything here. You get a global measurement of the temperature. You get a very rough idea of the morphology. If we move to 12,000 counts with the AXIS observation, for example, on the right, you can start to do a feedback study, right? And we can do that easily here. We can see the cavities. We can detect the inner ones at high significance. We can see the ones further out. You can also get radio profiles and all the gas properties. We can produce a pressure profile, and we can, having identified the cavities, we can measure the jet power. So this is really the game changer moving from these two, is we can actually do feedback studies in all of these objects. So an AXIS core science program, we'd be looking at around 850 kiloseconds, a core program to cover 20 targets. That would be at around 10 to sort of 200 kiloseconds each. I've sort of highlighted example targets on this plot here in purple, spanning 0.2 to 0.8 keV. So we're really sort of spanning the mass range and temperature range we'd be really interested in here, in getting this sort of much more representative sample of these lower mass systems. And we'd be answering the question, does AGN feedback regulate cooling and star formation in these low mass systems as effectively as it does in clusters? We want to look at the fraction of these systems with cavities. We want to look at whether the cavity power is well matched to the cooling rate, produce these plots looking at cavity power versus cooling rate, and much more besides to be able to do this. Obviously, we are also going to spend some time looking at the nearest brightest systems as well. We will obviously look at rich clusters, because with the PSF across the full view, this is just going to be spectacular. I've got, again, I'm using NGC 5813 here to sort of demonstrate, the advances in sensitivity that we're going to get. So on the left-hand side, this is the Chandra is 100 kiloseconds, and I've binned the image. So there's 1,500 counts per region. This is the kind of numbers of counts we need to be getting at the gas properties. In the middle panel, the same idea again, but for AXIS. And now you can see we're actually able to then resolve all the feedback structure in here, which produces the temperature map on the far right, where we've got the temperature structure on the scales of interest. We're resolving the gas properties on the scale of all of this feedback structure. So we can see the shock fronts, and the temperature map, we can see all of the bubble activity at the center. We can see the cool metal-rich gas flows being pulled out along the bubble axis. We can see all of this fantastic detail in just these short axis exposures. We'll obviously be looking at all the additional pairs of the relic bubbles to look at the full history of the AGN activity, look at the fate of the bubbles in many cases. Are they all piling up somewhere? Are they getting disrupted? Look at metal-rich gas flows, thermal instability, much more besides. So I just go through my conclusions. Axis is going to reveal how feedback operates across the whole gamut of hot atmospheres from these Milky Way mass sort of systems all the way up to the richest clusters, of course. The core science program would be looking to observe about 20 early type galaxies from the Atlas 3D survey in particular, and answering the question of whether feedback operates with similar efficiency that we're finding in clusters, but really on the much more challenging short gas cooling timescales of galaxies. Thank you.
Great talk, Helen. That was really fun to listen to. So if people have questions, if you want to just ask them or raise your hand or post them in the chat. So I'll ask a question. I mean, it's really interesting to see sort of the correspondence between, you know, cooling and AGN heating. And I was just thinking about, you know, you kind of get a history or profile, like you were saying. So when you have those cavities and you can say maybe millions of years ago or whatever, I mean, is that kind of how you figure out how this sort of happens, that you get this tuning? I mean, I guess in some sense, you're just trying to figure out why they don't seem to agree. But I was wondering about sort of the history of AGN activity. Yeah,
so if we start to detect multiple series of cavities, which you would certainly be doing for the brighter systems on there, and I'm hoping for some of the low mass systems as well, then yes, you can start to chart the history of feedback in a particular system. So you could look at the frequency of outbursts and say much more about the duty cycle. And yeah, you'd be able to look at more about how the energy gets distributed, what kind of radius are these coming out to. With Perseus, I think the sort of appearance is that they're starting to pile up at a particular radius, but I mean, we can't see that kind of detail in systems beyond Perseus at the moment. So really, we want to be able to do that in many more objects to try and say much more about how this energy is getting injected. Can we see sound waves in more objects? You know, the number of objects we can do that in at the moment is so very limited. I don't think we'd be able to detect sound waves all the way down to individual ellipticals in much more faint systems. For those, we're really looking at the bubble activity, but that we'd be interested to know really where is the energy coming out? Is it all in these bubbles? They do a huge amount of work, and if you just consider those, you can compensate for gas cooling in these systems. But maybe a lot of the energy is coming out in much more distributed way in sound waves as well. So there's huge scope for this here.